Hi, welcome to the third in this series on the mathematics of evolution, and my thanks for your sticking with it. I think we're coming up to one of the most fascinating parts of this presentation when we get into game theory, because here's where mathematics shows us things that ordinary verbal Darwinian theory really has a job in trying to explain, and the math explains it. Well, at the end of the last part of presentation 2, we were talking about the equation of replicator dynamics, and we basically were able to relate the size of a population and population growth with fitness, and fitness was the growth rate. I'd like to illustrate that very quickly at the beginning of this presentation, just to wrap up that idea with a little contest, because all evolution is involving contests for survival and contests for reproduction. Now, here we have 4 little rabbits. They're all different types of individuals with different characteristics that give them a different basic fitness. The blue guy has a fitness of 6, yellow 5, the pink chap has 4, and green has a fitness of 3. Now, what I've done on a spreadsheet is I've plugged those fitness values, 6, 5, 4, and 3, into 4 equations. Each of those is an identical equation, that is, they're the replicator dynamics equation, but we're tracking the population of blues, the population of yellows, the population of reds, and the population of greens. Now, it doesn't take an Einstein to predict what's going to happen here, and if anybody knows Darwinian theory, it's survival of the fittest, and we expect to see the blues become the most fit. Here's the results of the 4 simultaneous equations that we showed in the previous slide, basically tracking the population of these 4 rabbits with different fitnesses, and as we expected, it is survival of the fittest. Although the yellow rabbit had a bit of spurt sort of into about the 5th generation, all of the less fit individuals than the blue rabbit died out after about 35 generations, and 100% of the population was blue rabbits at the end of this time. This is mathematical proof of our Darwinian expectation of survival of the fittest. But all contests aren't quite as simple as this, with individuals whose fitness stays exactly the same through all generations and all situations of competitors that they have to face. With the rabbit example, we made one simplifying assumption, and that was that the fitness of the rabbit types stays fixed throughout their life. And at first it seems a pretty reasonable assumption to make, and it does sometimes happen in nature that way. But most often we find that fitness is affected by the contests that individuals have with one another in the struggle for existence. For example, if 2 individual animals are fighting for some food and one animal gets the food, at the end of that contest, the animal that got the food is going to become more fit than the animal that lost the food. And this is the typical situation in most animal contests. Fitness is the number of offspring produced in the face of competition. The reason that game theory got introduced into biology at all came about from trying to find an explanation to a problem that nobody seemed to be able to deal with in conventional Darwinian thinking. There were 2 significant individuals in the behavioral studies of animals, and that was Konrad Lorenz and Nico Tinbergen, and they were both trying to explain why animal contests are so very odd. What I mean by odd is that animals do not fight to the death, or they don't fight even to the point where one of them seriously gets injured. Well, Konrad Lorenz had proposed that the reason why animals had evolved that way was essentially for the good of the species, that it was a behavior that helped allow a species to be more stable and to reproduce more successfully without large numbers of its members being hurt through these horrible contests. Well, John Maynard Smith of Sussex University, who had studied Darwin a lot, just couldn't go along with that kind of thinking, basically because in Darwinian thinking it's really every man for himself. Evolution takes place at the individual level and not at the group level. So what Maynard Smith decided to do was to apply the mathematics of game theory to the problem of animal contests, to essentially calculate the fitness of animals depending on the way they fought, whether they fought aggressively or whether they fought with a little bit more care. What Maynard Smith did was apply a little bit of algebra to the problem that he was facing on animal behavior in contests. And he was trying to understand two basic strategies: fight or not fight. He gave the fight strategy the name hawk strategy and the not fight strategy the dove strategy. He did this work during the Vietnam War, where these kinds of terms, hawks and doves, were going around quite freely. What does a hawk do as its basic strategy? Well, the hawk is a fighter, and he'll escalate after a bit of a show into a fight, and he's only going to quit that fight if he's injured. The dove will try it on a bit, do a bit of display, try to share with the other individual that he's in a contest with, but as soon as it's really getting into a fight, he'll run from the fight. So those are the two basic strategies. And the variables of algebra that Maynard Smith used was B, the basic fitness that the two strategies had at the very beginning of a fight, then V, the value of resource that they were contesting for, and C, the cost of losing. Now, there are four situations when you have a pairwise contest like this one. You can be a hawk and you can meet a dove. Well, you're going to be able to get the resource completely. So your fitness at the end of that is going to be the base fitness that you started with, B, added to the value of the resource V that you got. So F fitness equal B plus V. If you're a hawk and you meet a hawk, well, there's guaranteed to be a fight. And you're going to win half the time, you're evenly matched. You're going to win half the time, and you're going to lose half the time. So the resulting fitness will be the base B that you started with, and for the times you win, you get V over 2, and for the times you lose, it's minus C over 2. If you're a dove and you meet a dove, you will be sharing. And so your fitness is going to be your base fitness plus the value V divided by 2. If you're a dove and you meet a hawk, well, he's going to take that resource from you, but you still can leave the contest with your base fitness intact. And that's basically all there is to the algebraic analysis of what the fitness is at the end of a contest. And what was done then is that these contest algebraic equations were plugged into the replication equation to produce a solution for what is going to be the survival of hawks and doves. And this led to a rather interesting surprise. What happens is that if the prize to be won is of less value than the cost of injury, which is the normal case in nature, an injured animal is normally quite defunct, the strategies will coexist in a state of equilibrium, and that state of equilibrium will have the doves in the majority. It's 80% dove, 20% hawk in our case. And this happens no matter what the mix of the population is to start with. This equilibrium point is called the evolutionarily stable strategy point. Maynard Smith had explained what Lorenz and Tinbergen couldn't explain, and he explained it with mathematics. And he's widely recognized, in Richard Dawkins' terms, for instance, as making an advance in the understanding of evolution that almost ranks with the basic principles first outlined by Darwin himself.